Okay, great. Thank you so much for inviting me here. It's a great pleasure to be back at IAIFI. I was here at the first workshop, and it's great to see its continuation to the third workshop. So you might have noticed that I have changed my title to this new one, Scattering Amplitude, a new playground for machine learning. So this is because I want to shift my talk to a new focus where I want to introduce this fantastic new problem space for machine learning to explore. So the goal for today, my talk is to introduce enough physics background for you to understand this particular data set, and also to show you our first attempt to tackle with this data set, the success we have and the pitfalls, and so that at the end of the talk, you may be able to just download the data set and play with it and have fun and beat our team. Okay, so
really hard.
So first, let's meet our fantastic team. So this is a great example for academia industry collaboration. So on the academia side, we have Lance Dixon and me at SLAC, and from University of Wisconsin, we have Kaya Kramer and also Garrett, who's in the audience. And he also gives a poster on Monday. So if you have any questions, I might just direct you to the Garrett. And on the meta side, we have the transformer expert Francois Schaffen and his previous postdoc Nicholas. And also we have Matthias from Niels Bohr Institute for the expert on the scatter amplitude. So we just have our very first paper published in May. So if you don't want to listen to me babbling for the next half an hour, so you can just check out this paper. And there's an open data set in this paper, so you can just download the data set yourself. Okay, great. So I want to start my talk with a relatively non-traditional approach. So I want to just give you, let you take a look at the data set itself, and without giving you any physics background. So let's do it as how AI is approaching the problem. So what you will see in the next click is a snippet of the loop 5 symbol. You don't need to know what loop 5 mean, what symbol mean. I will try to explain that in a second. So be ready. So this is your data set. So I will give you 10 seconds to stare at this data set before we move on. Right? So what do you think? So don't be shy. Just shout out with whatever you see. First, I will just do the first thing. So this seems to be pretty different from the usual data that we see in collider physics or in astrophysics or cosmology. So in some sense, this is symbolic data, although we are still far away from doing really symbolic manipulation, as Matt was suggesting on Monday. So what do you see? What is this?
I see SBs.
Okay, great. Nice. Okay, so first you see, this is a very, very, very large polynomial, which includes 100,000 terms. So I guess everybody sees some numbers, right? Some numbers, and they look like they are only integers. Right? And there also seem to be some positive numbers, some negative numbers. And somehow they seem to be all divisible by 4. Good, that's all we have on the number side. And we also see a list of letters. So if you really stare closely, you will see the letters are only from A to F. And so in total, there are only 6 letters. And if you do the counting very carefully, you will see, okay, in every SV list, there are 10 letters, exactly 10 letters. And magically 10 equal to 2 times 4, 2 times 5. Okay, very magic. And it also seems like there are some rules that govern which letter can appear to next to each other. For example, some very simple rules is if you stay at the very first letter for each list, it seems that everything starts with only A, B, and C. And if you look at the very last letter, it seems that everything ends with D, E, F. Great. So congratulations, you've just discovered many clues without even knowing anything about the physics of this data. So the next question is, what do we actually want to do for this particular data set? Very simple answer, we want to solve this huge polynomial. So by saying solving this huge polynomial, what I mean is that I want to find the correct integer coefficient corresponding to every SB list for letters at each given loop order. So more ideally, we want to find that polynomial for higher loop order. So the tip is once you go to higher and higher loop order, the polynomial will grow more and more gigantic. So it's harder to solve. So currently, by human experts, the highest loop order we can solve is 8 for a particular toy model. So ideally, we want to go beyond 8. And if we become more ambitious, we want to solve those polynomials once and for all. So that means we need to discover more rules about what is governing for those solutions so that we can obtain all the solutions to all loop order. And hopefully we can also try to extract some physics from those rules for us to help us to better understand the analytical structure of the amplitude we are studying. So the reason why we want to do all this is that we do not want our theoretical prediction to become the bottleneck for our future collider experiments. Of course, you can argue we are very far away from actually moving to the real realm of QCD. But anyway, so the whole hope of this amplitude bootstrap program is to try to go to as high loop order as possible. So I would say for the first goal we have here, this is data mining for direct answer prediction. So we don't care that much about the rules, but we want to get the correct answer from the inputs. And for the second part, this is more of data mining for pattern discovery. So what we want to discover more rules hidden behind those this data. So to accomplish this, we believe we need both human intelligence and artificial intelligence to collaboration with each other. Good. Now that we have first in the data, let's take a look at what is exactly the underlying physics. So for the data I showed you, this is for this particular process, the so-called three-gluon form factor. So the final diagram is shown here. In the real world QCD, this process has been calculated up to 2 gluon loops order. So like here. And however, if you're willing to go to a toy model, which is a simplified version of the QCD, it's cousin called planar and equal to 4 super young mu theory. This analysis process has been calculated up to 8 gluon loop order. So just to give you an idea why going up to higher loop order makes things much more complicated. If you stay at the tree level, the only functions you will encounter in your amplitude solution are rational functions of your kinematic variables for the three gluons. Once you go to one loop, you will encounter special functions like logarithm, which is defined here. And if you go to higher and higher loop order, you are in the best case scenario, you will encounter something called generalized polynomials. So we call the dialog function a weight 2 function because this is a function. There are 2 integrals over rational functions. And in general, if you have n integrals over the rational functions, you will have a weight n polynomials. So the nice thing about this planar n equal to 4 super young mu theory is that at a particular loop order L, you have all the functions you have for n equal to 4 are of uniform weight to L. In QCD, however, you will get all the functions from weight 0 up to 2L. So that is one of the reasons why we stick with n equal to 4. There are many other reasons. Okay, so very fortunately, we have our friends in the math department who have spent years to study those wild functions. And one of the great tools they come up with is called symbol. So remember the definition for the polylogs, for the general polylogs, the function involves a lot of integrations. So when we want to study those functions, what we do is we take derivatives. So for example, if you take one total differential for this function f of weight n, you will get an expression like this, where this function f as k is just going to be a function of weight 1 lower. So if you iterate this process n times, you will get the symbol of the function. So in this case, your this will just be an n-fold tensor of rational numbers only. And this tensor product is just a shorthand notation for this b log Sn. And physicists are even lazy, so sometimes we omit the tensor product and just show things like this. So to give you an example, if you have this general logarithm, if you take n differential and if you bleed me, at the end of the day, you will get something like this. And in this case, your single alphabet just contains 2 terms, 1 two different terms. One is x and one is 1 minus x. So this is for this particular single case for the dialog. So let's take a look at what the symbols are for the process we are studying, the three-gluon form factor. So it turns out this three-gluon form factor in n equal to 4 is maybe the simplest possible symbol you can ever have. So this symbol only contains 6 letters, as we've already seen in slide 1. And these 6 letters are nothing but the rational functions of the underlying kinematic variables. Definition given here, but we don't really care about that. So here I give you 2 examples for the symbol at loop 1 and at loop 2. So at loop 1, it seems very simple. There are only 6 terms, and all of them has coefficient -2. And at loop 2, there are a bit more terms, but they all seem very manageable. However, if you look at this table, this is how many terms you will have once you go to higher and higher loops. So naively, if there are no relation whatever in the terms for the symbol, then at each slot you will have 6 choices and you have 2L slots. So that is why the naive count is 6 to the 2L. And in reality, what you see is that the non-zero terms for the actually appearing in the symbols is much less than the naive count. So it's 10 to the 3, much less than for the loop 8. So still there are many terms, and it is not really recommended for your naked eye to stay at the single terms. So that's where we think machine will help. Okay, so I mentioned that the actual number of terms in your symbol is much less than the naive 6 to the 2L count. So this hints at there are many rich patterns hidden inside the single terms. So one of the simplest pattern we have is the so-called dihedral symmetry, and this is nothing but by the definition of the letters themselves. So basically, you can draw this triangle, and if you do the cycle and you do the flip, the coefficient for those cycled and flipped words will be exactly the same. And there are also some rules that you already discovered in slide 1, the prefix and suffix rules, and also some very simple adjacency rules, which says you can't have an A next to a B and also D next to an E in the actual images. So all this means whenever you encounter a word that has A and B next to each other, the word will have a 0 coefficient. So let me give you a relatively more non-trivial example. So a symbol has to be a symbol of a function, and a function has to satisfy certain relations. One of the relations is that the mixed partial derivatives must commute. So that requirement translates to this particular relation over here. So to give you an example about how to read this relation, so this is saying, okay, I can have AB, AC, BA, CA at any slot in your word, and all the other slots have to be exactly the same. And then you grab the coefficient corresponding to these words, and then you add them up, and you find that they should sum up to 0. So there are many more relations like this hidden within the data, and one of the goals we have is to try to discover more relations by using a machine. Okay, good. Another look at this loop 5 symbol. So we know the ingredients of the symbol is that we have integer numbers, we have 6 letters, and each single term is an integer coefficient plus a 2L lettered words. And if we think of each single term as one data point, you can see we have a huge amount of data to be mined. Okay, great. So now we've at least learned something about the physics behind the data. Let's try to see how we might set up the space for the machine learning application. So our first attempt is to use a supervised learning framework. Because our problem is completely discrete, you just have letters and you have integers. We think maybe using the natural language processing translation problem will be a very good approach. So what we do is we tokenize integer coefficients and words, and all of them just become unique tokens. And then all models are trained to minimize token-wise cross entropy against the truth. And then we train a model on a fraction of the symbol and then evaluate the model on the held out test set. So the particular architecture we tried in our first paper is a transformer, and these are the details of the transformer. So indeed, our transformer is very small comparing to all the industry transformer, which has trillion of parameters. But what I want to stress here is that the result we have is like not limited to transformers. Indeed, we tried many other non-transformer NLP models, and they don't give any qualitative difference results. So again, the key thing we want to do is not for performance optimization for this problem. Indeed, what we want to do is we want to better understand the underlying structure of the data, and then to have at least a first machine learning pipeline set up for this new problem. Okay, so when you use natural language processing, so one of the most important thing is what's the tokenization thing we use. So for us, we have again a very small vocabulary, and it's relatively easy to tokenize a letter. So each letter just corresponds to one unique token, and also same for the signs. The coefficients are actually a bit tricky. So the reason is because of this. So right now, how we do the coefficient tokenization is that we just tokenize the coefficient of digits in base 1000. So for example, this number is then becomes this particular thing, and 1 to 3 is one unique symbol, one unique token. So the reason why this is a bit tricky is because as you go to different higher and higher loop order, the distribution of your coefficient actually shifts. And also the coefficients, the number, the actual integer becomes much larger if you go to higher loops. So that poses some difficulty for this particular coefficient tokenization. And I want to mention that there are many other ways to tokenize integers that we also tried in our paper. And also there were ways to compress a word. We also tried that in our paper. So another thing to say is for now, an incorrect coefficient is just incorrect, whether it is wrong by 1 or by 1000. Okay, so we come up with two tasks to test our machine. The first task is probably the simplest ever possible task you can think about for the supervised learning. So basically, we have a training set at a particular loop order, and we let the model see the word and its corresponding coefficient, and then at test time we give it another word that the model has never seen and ask the model to predict the coefficient. So again, this is the most classical supervised learning setup we can think about. Okay, the second part is that we want to ask a question that if we know the coefficient for the lower loop, can we predict the coefficient for the higher loop? So for this, we come up with a little bit more dedicated training. So what is showing here is, say you have a word at say loop 2, AAAF, and you know that word corresponds to the coefficient 16. You want to relate this particular word to some parent word at one loop lower, which is loop 1. So what you do here is you just strike out 2 letters from your word. So for example, if you strike A and A, what you get left with is AF, and you look at what the coefficient corresponding to AF is, it is -2, and etc. And the input to your model in this case becomes this list of coefficients, this list of integers, and the output is the actual coefficient of the parent of the child word at the higher loop. So at test time, you give it a new word as the 2 BFFF, and then you do the strike out and obtain all the coefficients for the parents from one loop lower, and then ask the model to predict what the coefficient corresponding to the BFFF. Okay. We also want to assess whether, so there are many relations that we humans already know, and we want to know if the model are utilizing those coefficients. So what we do is we design an auxiliary test set composed of several hundred instances of each relations. For example, for this particular relations, we construct this instances and to evaluate if the model has predicted correctly on this particular relation instance. And these are the metrics we use to evaluate the model success. So I will show you, explain more when I show the results. Okay, so now let's look at some talk from the other results from the transformers. So this is doing the first task, predicting predicting the coefficients of words at group 6. So what you're seeing, so these are the implementation details, but what you're seeing here is the accuracy, prediction accuracy over the epochs. So there is this very interesting two-phase learning dynamics that we observe for any models we train almost. So what is showing here is that the model learns the magnitude of the coefficient first, and then it learns the sign. And before the model learns the magnitude, before the model learns the sign, the model actually prefers to predict one sign over the other in each epoch. So that is why you see all this fluctuation in the plot down here. So this is very interesting because it shows that somehow it seems that predicting magnitudes is an easier task than predicting the signs. So so in order to better analyze this, we take a look at what the model is actually doing for those relations. So there are three groups of different performance for the model for the relations. For one of the group 1 relations, those are the equivalence relations, which requires two coefficients to be exactly the same. So here you can see the red curve is when the model gets the relation correct, but regardless of the individual coefficient prediction, we can see the model almost immediately correlates these two terms together and know that these two terms should have the same coefficients. And on the other hand, for group 2 coefficients, for the group 2 relations, because in this relation, at least one particular term should have a minus sign relative to the other. So that is why the relations are learned at the same time as the model learns individual coefficients. And group 3 relations are just a mixture of group 1 and group 2. So it seems that the model, what is very interesting here is that it seems that the model is able to find the terms that are related to each other and instantaneously tell you, okay, these two terms have to have the same coefficients. And the other thing we did is we looked at the embedding space for the letter tokens from the transformer. So what you are seeing here is we get the embedding vectors from this embedding space, and we see that those embedding vectors for the letter A, B, C, D, E, F, they actually obey both the cyclic and flipped symmetry. And what you're seeing here is just we project that down to the three leading TCA space. So this says the model actually learns the diagonal symmetry from the data. That's really interesting. And the second task we have is to predict the next loop single. So the result I'm giving you is predicting loop 6 single from loop 5 single. And again, this is how we construct our training and test data sets. So you can see here, the model is able to do very well on this task. And here we do not observe this two-phase learning dynamics. So everything is just learned at the same time. And we studied many other variants in our paper, but the interesting question to ask is that, are we able to recover some symbolic formula connecting different loop orders? So far,
Go ahead, I'll ask it.
okay. So far, we do not have any success with AI models, but we do have some success with humans. So inspired by the AI models, humans are now able to find a few more correlations between different loop orders. So this is going to be some results from soon to be published paper. So what this says is if you look at a particular type of word, the word is B followed by a bunch of D, and you look at the coefficient for that, those coefficients are actually connected with each other by this particular formula. And this is confirmed by loop 7 and 8. And we find many more sequences like this. And what is good about this is that if we can find more sequences like this, we can use them as the seed terms for the AI model once we go to, say, loop 9. And we can assume that those terms we already know. And on the other side, we want to ask, can AI really help us to detect more such sequences? Because if yes, then we can better find our actual single data. Great. So I want to give you some of the challenges we are facing for using this supervised learning approaches in case you are interested in playing with the data yourself. So one of the biggest challenges we have is if we move to a higher loop order, say loop 9, we do not have enough training data. So for loop 9, we do not have, say, millions of terms already known. But if you want to use the supervised learning approach, you do need at least some training data, right? So this is one of the obstacles we have. So that is why it is very important for us to be able to generalize a model trained at lower loop to a higher loop order. It turns out that at least if you do it naively, it is very hard to do the generalization. And it's mainly because of the two reasons. One is that at different loop orders, the words have different lengths. So there is this length generalization issue, especially if I transformer, but this one can be relatively easily solved. The harder question is that the coefficient itself becomes larger and the underlying distribution for the coefficients are different. So here there is this very annoying domain shift problem, and I'm not sure if this is easily solvable problem. So the question we want to ask is that within this supervised learning framework, is there a better way to utilize all the data we have so that we can train a model to easily generalize to higher loops? So one initial thought we have is that we can design a training strategy that is focused more on the relation data itself that we know is valid across all loops instead of just focusing on the individual terms as we are doing now. So for this, one possible solution is to maybe design a foundation model for all loops, and this is ongoing work. And I also want to say that you don't really need to stick within the supervised learning approach. You can try some generative model approaches, and indeed we are trying reinforcement learning approaches, but it's just a very initial stage. So a big warning though, for all this approach based on data, what you need is once the AI or any model give you a prediction of this huge polynomial, which might include billions of terms, you need a way to verify whether the model prediction is correct or wrong. So you need a way to say, okay, which terms are wrong, and how do I actually correct the wrong terms, and how do I improve the model prediction based on the previous training. So in principle, this can be done, and in principle, it is easy, but everything that is in principle easy is very hard in practice. So it is pretty hard to really implement this, and we are trying to do something, design such a verifier now. So I want to give you a more broader conceptual picture for how we want to approach this problem. So on the one hand, we have this human-based intelligence approach, which is more top-down and analytic approach. So basically for this approach, we use non-relations to restrict the function space as much as possible. And if we have enough relation, then we would be able to narrow the function space down to exactly one point. And that point is presumably the actual single answer. And for now, we are able to do that up to 8 loops. And once we get this one point, we just check this reduced single against certain boundary conditions to see if everything we did here, all the conjectures we put in are correct. So this is a top-down approach. For the AI side, we have this bottom-up data approach where I just give the model enough data and I just let the model to directly predict any new terms. And the input-output pair is all I care about. Of course, a model may implicitly learn some relations, known relations or unknown relations, and the model can leverage them to make predictions, but our focus is not on the relations per se. So as you can see, there is a very great collaboration happening between this human approach and the more AI approach. So for the human approach, once we find more C terms, we can use them as training data for the model. And on the AI side, if we can extract new relations from the database model, then we can use them to narrow down the solution much more efficiently. So what we hope in the far future is to build an amplitude oracle so that you ask it for a loop order and it will just give you the answer. Of course, it is far down the road. And at least we hope the AI will serve as quoting someone else's quote. It will serve as a resource for inspiration and agents for understanding. So before I end, so here are the papers, and also here is the data set. So in case you're interested, please just go ahead and download the data set. And if you have any questions, just you can email me or ask Garrett. Thanks.
Have you any questions about it? You can decide as well.
Ah, thanks, very nice talk. I think I may have missed which field theory were you testing on? Which field theory? What particle?
Oh, violence any force. So just a kind of,
Scalar,
what's that?
scalar particles?
Mm-hmm.
So how close are you, very nice, by the way, I like your technique. How close are you to testing this on something that, you know, is of, you know, that we see in colliders like Higgs to lepton here?
Okay, very
Maybe
far.
you even try that, I don't know.
No, it's very far away. So the reason is, one of the reasons is because if you go to QCD, say, in your solution, you will have functions all the way for different weights. So right now in this particular toy model, you only have functions at weight 2L. So that is one reason. Another reason is for QCD, we only have data up to 2 loops, and that is because we don't have enough boundary conditions as well known as in n equal to 4. We don't have enough boundary conditions to constrain this solution.
So even QED is not feasible. Not yet, okay,
Not yet.
looking forward to it, thanks.
Not yet.
Okay, so I have two questions. So the first is, so imagine like 30 years ago, before we knew the Park-Canada formula, you were trying to, and we had transformers 30 years ago, you were trying to predict the coefficients of all of the, you know, ordinary like QCD gluon amplitudes in terms of all the tensor structures. But that was the wrong basis because if you use standard helicity, it was just one term. Do you have any reason to think that this might be the wrong basis?
Yes, so we are testing this on different bases as well. So I didn't have the time to go into the details. So I mentioned that there is different ways to compress the words. There are also different ways to construct the words itself. So one of the ways is to, instead of using this a whole word like this, we are able to compress a word in terms of the front space and back space, and then there's just a sewing matrix in between. And then in that case, we can just try to predict the sewing matrix in between. So yes, to your answer, yes, there are different bases, and it's not guaranteed. And sorry for that. Yeah, I'll just shout. But yeah, the short answer is yes, there are different bases and we should try it on different bases. This is one particular basis, and this is nice because all the coefficients are integers. So it's very, at least in this format, it's very hard to find another basis which gives all the integer coefficients. But yes, there are other bases.
The second question is, so there's been some nice work at Anthropic in trying to do interpretability of transformers by training a sparse autoencoder on the NLP outputs in order to sort of identify, like, you know, which things are firing on which, you know, kinds of words, you know, languages, numeric sequences. Like, you guys it might be interesting to look into applying that to sort of open up a little bit of the black box of like what's actually.
Yeah, it will definitely be interesting for future. So right now we did a very, very simple analysis for trying to open the black box, and that is kind of all we can get from looking at the embedding space. But we definitely want to do along that way, and also try more about the symbolic regression, different symbolic regression schemes to see if we can really understand extract some physics.
I'll be fast. Nice talking to you. So simple question. I think I just don't know enough about the context. In these large theoretical data sets, when you're doing a search problem, which is effectively what you're doing, you're searching for the coefficients that are the right solution. It's nice to have fast checks, fast verifiers, where you can verify at polynomial time that the proposed solution is correct. Do you guys have that in this case? I think I missed that. You don't.
No.
Okay. So there's no in principle way to know if it's right.
Right now, no. So right now, what we do is we just track it against the true, the ground truth, and that is only feasible because we know the ground truth. So in the yeah, in the future, one of the way we want to do this is to track it against the boundary data, like the data we have from OPE. So that's something we can do, but right now it's not implemented yet.
Thank you.
Sorry, I'm not familiar with the field, but I couldn't help asking. It sounds like that you have large expressions that you want to reduce or even find out if they're correct or not. Is there any attempt done in the past using something like a grammar-based compiler to go through this kind of large expressions?
Can you elaborate a little bit on the grammar bit?
So, if you look in the open source, there are tools called Lex and Yak, which essentially create grammars.
Yeah. Yeah,
There
so-
have been, okay.
Yeah, we are trying this, and this is more along the way of building this verifier to just automatically check whether the grammar is correct or not. So right now, what this is trying to do is to try to find the solution itself without doing all the linear algebra thing. So I guess for the Lex and the X, what they are really good at doing is once we have the solution, can you check if the grammar is correct or not? So we are doing that. Yeah.
So you're trying to find missing expressions and find those expressions that you need to put in.
Yes, so we want the model to give us one such a guess answer, and then we can check whether the guess answer is correct or not.
Hi, so I'm curious, so to what extent this generalizes between theories? So you can say you train this to 5 loops on super angles. Can you then fine tune it on say like 2 loop QCD using the strike through method or something like this?
It's very good question. That is what we hope for the Amplitude Oracle. And that is also why we are right now trying the reinforcement learning approach, because it is more possible for the agent to translate the agent from a particular environment to a different environment. And there I am more hopeful that the agent will be able to do that. But yes, that is for future analysis.
Thanks for the beautiful talk. So at the beginning, you showed the number of terms at each loop order. It's like quickly get around a billion or trillion, I can't remember. So it sounds like and for whatever model, if you can achieve even like 99.99999% accuracy, you still get a huge number of terms wrong. Like, I just wonder like what your visions or ambitions are in this program for like, given that this is just the scope of the problem of this intrinsic challenge of the like exponentially number of terms.
Yes, that's a very, very important critique. So for me, I think that's why I mentioned this is very important for the human and the artificial intelligence to collaborate with each other. So it would be very difficult to design a model that can predict all the terms exactly correct. However, it would be more easily for the model to find rules from the data. So right now, all the rules we find is more or less by human inspection, like eye inspection. So what we hope is that we can design models that can make most of prediction correct, and then we can extract the rules from the model and then use those rules to do this top-down human approach. Because only from the top-down human approach can we be very certain that the answer we get is exactly correct. And also designing the verifier is going to be very messy.
No question?
I understand the physics reason for task 1. Like there is a correct answer for the amplitude, and like this is in relation to like, trying to find that correct answer makes sense. Is there a physics reason why you think task 2 should be possible? Like what's the physics reason why we should be able to predict exactly the next loop amplitude from the previous ones? Because like in QCD there's no reason necessarily for that to happen.
Yeah, one of the reasons we expect this to happen is we don't expect it to be exactly predictable, but we do expect to find more relation, like cross-loop correlations. And that we do actually find inside by model, but not by the model, by humans. Yeah, so I would say going forward is actually not going to be really efficient, really sticking with this half-moon paradigm because you do not have all those training data. So it is very important to have a model that is able to at least transport the knowledge it learned from the lower loop to higher loop. So that is going to be very, very important.
Okay, so it, like, if that's true, then it can never be a full oracle, because you could never say, like, compute me the 9-loop amplitude without any data at 8 or 7 or 6 or whatever. You have to seed it with something.
Yes and no. If we can find everything for this, something like this, if that is suitable for all the words, then yes, we can find everything to all the border. But of course, I do not think that is really doable.
No questions?
But also, even for an oracle, we don't really need to be like this. We can have a recursive relation. So.
I guess my question is similar to Yoni's in spirit and is a little off the cuff because his question just got me thinking about it for the first time. I mean, so there's a loop expansion in quantum field theory, and the question of whether you can go from one loop to another, a higher loop using only lower loop data feels like effectively the same question of the extent to which you can figure out the generating function of the loop expansion from like fixed loop order data. I guess I have no sense of whether that should ever be possible or not, but I'd be curious to hear if you have a comment on it. It seems hard.
I don't think it's ever possible, and also this is like if you just look at the coefficient level, it's like you have this distribution and you wanted the model to be able to generate a distribution which is kind of not entirely different, but very different from the current distribution. So that is why we think it is not possible. But what we hope is that we can have a model that has all the knowledge it can ever gain from the lower loop data, and then transport that knowledge to the higher loop data, and then maybe we can fuse that with some additional human non-C terms or whatever, and then the model is able to predict as many terms as possible. And then we can try to design a second model, like a verifier, to try to correct the wrong terms and try to fill up some missing terms.
As long as I have the mic, I might as well just comment briefly that this sort of problem of predicting integers that are sort of sparsely populated like this is very similar to certain number theoretic problems that appear in algebraic geometry and string theory. Generally, they're very hard because the numbers are sort of very sparsely populated. But you might, I don't know if you can visit, but you might pay attention. There's an ML for Math program going on at Harvard all fall where there's going to be mathematicians and AI people thinking about these sorts of problems because they're classic, the data sets are there, and it's still generally very hard to do such things.
And we also draw a lot of inspiration from the math community. Yeah.
More questions? Let's do. We can thank the speaker again.